Hi. I wanted to add something to what I told about weak solutions. So, our equation is this. It is the same string equation, and we consider initial value problem. U for t equals 0 equals f of x, ut for t equals 0 equals g of x. And but now let us consider the situation when the initial conditions are very, very singular. Namely, consider first f of x equals delta of x and g of x equals 0. Yes. So all our initial function is concentrated at 0. This is this way I describe the initial function f. Then we write u of xt equals 1/2 f of x plus t plus f of x minus t equals 1/2 delta of x plus t plus delta of x minus t. So in the xt plane we have these two diagonals or two characteristics, and solution is concentrated on these characteristics. So at every moment t we have one delta function, 1/2 delta function here and 1/2 delta function here. Yeah. So I would say solution at the moment t looks like this. It is t, it is minus t. And so when t grows, this point goes right and this point goes left. No, it looks quite fantastic, but we can return to the definition of weak solution. Weak solution is a solution which can be approximated by smooth solution. So instead of this solution, smooth approximation, we consider the following solution. F of x equals phi epsilon of x, where phi epsilon is a function which is concentrated on the segment between minus epsilon and epsilon. Yeah. So initially we have this initial condition, yeah, like this. So it is concentrated from minus epsilon to epsilon, and the integral is equal to 1. Yeah, and for it is for t equals 0, and for t more than 0, we'll have these two bumps. It is t equals minus t. It is t more than 0, and it is 1/2 phi of x minus t. It is 1/2 phi of x plus t. And we see these two smooth waves, one is going right and the other is going left. Now it remains to say what does it mean that this function, which is a good, continuous, smooth, infinitely differentiable function, in what sense this function approximates delta function. Yes, delta function is 0 everywhere, and at one point it is not defined, or let's say infinity, but its integral is 1. Or in other language, it is not the distributed mass, but mass concentrated at one point. So what does it mean that we, how can we approximate delta function? It looks a little bit strange, but let me explain it. So approximation of delta function. We consider the following expression. Suppose we have the function, say, phi epsilon of x. Yes, and instead of considering values of this function at different points, we consider the following thing: integral f epsilon of x, say some function h of x dx, where h is some continuous function on the line. Yeah, so we consider this integral, and we can see that I have already showed you that integral phi epsilon of x h of x dx, what happens when epsilon goes to 0? Then the function shrinks to one point, in this case point 0, and the limit is just h at the point 0. Yeah, so because I explained it that the function h is continuous, so if you take sufficiently small segment containing 0, then the function is changing there very small within some delta. Yes, and delta goes to 0 as epsilon goes to 0. And so this means that this integral is between h of 0 minus delta and h of 0 plus delta, then delta goes to 0, and all this goes to h of 0. Yeah, but we know other thing, that integral delta of x h of x dx is just equal h of 0, because all the mass is concentrated at just 1.0, and if you multiply it by h, the function h of x, it was, the result will be h of 0 times delta function. So h of x times delta of x equals the same h of 0 delta of x, because outside of 0 delta is 0, and at the point 0, h is h of 0. Yes? So this means that after all that limit integral phi epsilon of x h of x dx when epsilon goes to 0 is equal integral delta of x h of x dx. Yeah? And this means that in this sense, in some sense, the function phi epsilon approximate the function delta function. Yes? Again, we cannot compare the values of phi epsilon and delta at the points of x because delta is a function which has no value at 0. So it's nothing to compare with. But we can compare these integrals. So in this case, we can say that it is not limit just, but weak limit. Weak limit of, no, it is limit. So I write that delta of x equals weak limit phi epsilon of x when epsilon goes to 0. In this sense, weak limit, no, similarly we can consider the function in the next example. So this way we more or less justified that this function delta 1/2 delta of x plus t plus delta of x minus t is a weak solution of the string equation, simply because it can be in the weak sense approximated by a smooth solution. Now consider the second characteristic problem. So again, our equation is the string equation, and initial condition u for t equals 0 equal 0, ut for t equals 0 equals delta of x. Yeah. So this time it is the function g is delta of x. F is 0 and g is delta of x. Now let us write down the solution. U of xt equals 1/2 integral from x minus t to x plus t delta of y dy. So, and now let us see what it is. Here is 0. So consider a point xt such that x plus t and x minus t are, say, positive. X minus t, it is x plus t. Yes? Then the function ut the function delta of I, here it is 0, because all this segment where we integrate it is beyond, does not contain 0. So here it is 0. So it is 0 everywhere it is x equal t. So everywhere here u of xt equals 0. Everywhere in this domain. And similarly in this domain it is x equal minus t. Here also u equals 0 in this domain. And in this domain, if you have a point here such that x is less than t and more than minus t, then the segment where we integrate contains the point 0. Yeah? So this means that integral from x minus, let me draw it on different picture. Here it is x minus t, this is x plus t, it is xt. And if you write this integral, we see that this segment from x minus t to x plus t contains 0. And so integral of delta function along this segment is 1. Yeah? No, we have this 1/2. So this happens when x is between minus t and t in this domain. So here u equals 1/2. So if you take the full picture, then you have this picture. Here u equals 0, here u equals 0, and here u equal 1/2. Yeah? And it is, let me denote it as a special notation, g of xt equals 0 if module x more than t, 1/2 if module x less than t. Yeah? Here module x less than t. For if module x equal t, I don't define it, and in fact it is not necessary because if you have a jump function, usually it has no the value of the function at the point of jump is not usually defined. No, there exist some special situations when it is important, but generally it is not important. And so this function g is called Green's function for the string equation. Why it is important? Now it's important because of the following formula, which is the same as it was before, but closer to the general formula for many other equations. So you have u tt minus u xx is 0, u tx0 equals 0, ut, t is 0 equals g of x. Yeah? And then you write u of xt equals integral g of x minus y t g small of y dy. Yes, we have this formula. What does it mean? If you take just one term for one fixed y, so the function g of x minus y t, it is this function, yes, which is a solution of the problem where initial condition is solution of initial value problem with g, say ut of x0 equals delta of x minus y. So delta, this point mass, which is put at the point y. And now we know that g of x equals integral delta of x minus y g of y dy, which I explained last time. And so this means that we can represent any function as a sum of delta functions and at all points, no, with the coefficient dy. Yes, and so and this means that solution is also integral of solutions with this delta function initial condition over all y, which is written in this formula. Yes, and now you can see that if you just write this formula, then you'll have the same formula which we had before, because if you take gxy, so integral g of x minus 1 t, g small of y dy equals integral of what? It is gx minus y. It is 1/2 if module x minus y less or equal than t, and 0 if lesser t, module x minus y more than t. Yes, integral of this function times g of y dy, and so it is 1/2 between x minus t and x plus t. Yeah. Equals integral 1/2 if y is more than x minus t and less than x plus t, and 0 otherwise. G of y dy. So we multiply the function g of y on this function, which is 1/2 in this segment from x minus t to x plus t, yes, and 0 otherwise it's the same as integral from x minus t to x plus t, 1/2 here, g of y dy. Yes, so in fact we have proved this formula without considering delta functions, which is I would call piano string. So consider a string, say from 0 to L. No, as usual, it is described by u tt minus u xx equals 0. And initial conditions are the following. U for t equal 0 equals 0. Ut for t equals 0. Let me write it minus L. It is 0L. So our string is from minus L to L. Technically it is easier. Ut equals delta of x. So this means that at the time 0, we say make a blow or an impulse at 1.0 in the middle of the string. Say no, practically in the pianos this point is not in the middle, it's closer to one end, but here for simplicity let it be in the middle. Yeah, so just a hammer, you know, in the piano we have a hammer which strikes the string and immediately goes back. Yeah, so it is just instantaneous impulse at one point. Instantaneous impulse. Yes, and what is the further motion of the string? It's interesting, and then compare it with the guitar string. So let us consider, first of all, replace this problem. No, we have to add boundary conditions. U of minus L0 of minus LT equals U of LT equals 0. So the string is fixed at the end points. This means that we, when we solve this problem, we can use the odd continuation of initial condition. So consider the problem VTT minus VXX equal 0. V x is in the whole line. V for t equals 0 equals 0. Vt for t equals 0 equals what? Let us find it. So it is 0, it is L, it is 2L, yes, minus L, minus 2L, and so on. So we have to, these are our endpoints. So we have to reflect it relative to these endpoints. So this point 0 goes to 2L, and we have to change sign. So here we have delta function, here we have minus delta function. The same is when you reflect it with respect to minus L. So here we have minus delta function. Now we have next point, which is it is 3L, it is not so interesting. We have to make a reflection with respect to 2L, yeah, 3L, and here we have again plus delta function, and at the point 4L. And here minus 4L, we have also plus delta function. And so gamma of x, it is gamma of x, it is the following: delta of x minus delta of x minus 2L, it is this point, minus delta of x plus 2L, it is this point, plus delta of x minus 4L, it is here, plus delta of x plus 4L, it is here, minus and so on, equals, in short sum, minus 1 to the power k delta function of x minus 2lk. Yeah, k from minus infinity to plus infinity. Yeah, so this is this function gamma of x. Now solution is the sum of solutions which are generated by these unique blows. So this means that solution u of xt equals the first term g of xt minus g of x minus 2l t minus g of x plus 2l t plus g of x minus 4l t plus g of x plus 4l t and so on. No, we don't need all of them because we'll see the pattern very soon. No, okay, it is better to draw a picture. It is the point 0, L, minus L, 2L, minus 2L, 2L, and so on. It is 0, and here is the t-axis. From here we have these two diagonals, x equal minus t, x equal t, x equal minus t. From here we have again two such, one moment, I have to do it more accurately, like this. Now from here it is 4L. It goes like this, minus 4L goes, just a minute. No, I'm sorry. L, 2L, 3L, 4L, minus L, minus 2L, minus 4L. Okay, so it goes the point this way. It is 1. Let me draw first these characteristics. Yeah. And now look, here we have we yes have 1/2. Yes, because here we can it is in the domain of influence of just 1 point, 0. So the other functions are 0 at this in all this square. Here we have from this point 0, here is 1/2, but from this point is minus 1/2. So here is 0 and here is 0. Now here we have 1/2 from this, minus 1/2 from this point, minus 2L, and minus 1/2 from 2L. So it is minus 1/2. Yeah? And again here it is minus, but here is plus, so it is 1/2. Here is also 1/2. Here we have again 0, because here we have it is in the influence of these, and this. So here it is 0, if you find accurately this sum. No, we don't need much because not anymore, because we are interested in this domain from x from minus L to L. So let me draw it in more detail, and then we'll see what is the motion of the string. Minus LL. This way, then this way, this way, okay, so here the solution is 0. From here, here it is 0. Here is 1/2. Here is again 0. Here is minus 1/2 everywhere. Here is again 0. And here starts in U the same thing. So we can now draw the picture. Yes, and the time moments. This is L, this 2L, it is on the time axis. It is 3L, it is 4L. So for t equals 0, we have 0. Let's consider t equal L over 2 here. then so t is 0. This is shape of the string. It is point minus L, it is L. And for t equals L over 2, we have the following picture. It is 1/2, it is minus L over 2, it is L over 2. And here it is 0. It is t equal L over 2. Now, for t equal L, it is here. So it is all like this. So you see, solution is discontinuous function, jump function, yeah? So here is also jump function. So this condition that u at the endpoints is 0 is broken here, not just at one moment. Now let us go up here. T equals 3L over 2. It goes back this way. Let me draw the arrows. They show the direction of the wave. Here the wave is going back. T equals 2L. It is again 0. It is here. Next, t equals 5L over 2. Here, at this moment, the velocity is again delta function. Then it gives rise to this rectangular wave, and this is t equals 3L. Again, it is like this. It is here. Now, t equals 7L over 2. It is going back. And at t equals 4L, it is again 0. And then it repeats. Yeah. So we can compare it with the guitar string, which I will draw now. So it is piano. And this guitar. For t equals 0, we have this shape. T equals 0. T equal L over 2. We have this shape. For t equal L, we have this shape. Yes, so it is 0. For t equal 3L over 2, we have this shape. t equal to L. We have this shape, yeah, and then it goes back. And so on. Yeah. So you see that the guitar string behaves much smoother. It is a more regular solution than the result of piano string, result of this blow at one point. And definitely it can be heard if you listen to guitar sound and the sound of guitar and sound of piano. Yes, maybe those of you who are more musical than me can hear it with their ears. I hope to have a chance to return to these matters when we will consider the Fourier method. Okay, now let us finish for now. If I forgot to tell something, I will tell it later. For now, have a good time. Bye.